Hello and welcome. Activity 2 is going to compare or try to determine some enthalpies of chemical reactions and compare some different reactions with some different methods and basis sets. So let's begin here. So we're looking at two different reactions. We're looking at formaldehyde plus O2 goes to CO2 plus water. So you're going to want to balance that reaction. Then do the same thing for acetaldehyde plus O2 goes to CO2 and water. And then we're trying to calculate their delta E, delta H, delta G. The way we would, of course, calculate delta E, H, and G is to evaluate each molecule in the reaction and then take the sum of the products minus the sum of the reactants. So the ordinary way of calculating delta H and delta G. And let's see, we're using methods like the B3LIP 6311 plus G2DP. This is a pretty big basis set, but these are also pretty small molecules. And then we're doing the same thing for both reactions here. Now, when you go through and you notice the second reaction has the same O2, CO2, and water, you obviously only have to run the calculation on oxygen one time. Same thing for CO2 and water. So we're really just doing 5 calculations here. We're doing formaldehyde, O2, CO2, water, and then acetaldehyde. And what you probably want to do is extract the results into maybe an Excel spreadsheet so you can actually do the arithmetic relatively easier there and then report the results in your table here. One issue is that when you're doing a calculation on oxygen, you might recall from MO theory, maybe back in Gen Chem, maybe in OChem, I don't know when you last talked about this, but oxygen has 2 unpaired electrons. It's pretty uncommon to find a stable molecule, or not a stable, it's not a good word. Whenever you find an uncharged molecule, usually the uncharged molecule is going to have 0 unpaired electrons. Like acetaldehyde has 0 unpaired electrons, CO2 has 0, water has 0, but oxygen has 2. The multiplicity of the molecule is equal to 2 times the total spin of the molecule plus 1. So if the total spin of the molecule is plus a half for each electron, so 2 unpaired electrons, so the net spin is 1. So you take 2 times 1 is 2 plus 1 is 3. So that's a triplet. So that means we have a triplet ground state for oxygen. So we have 2 unpaired electrons or a triplet ground state. Now, singlet oxygen would be the case where we have 2 spin paired electrons in the molecule of O2. And that you can actually play around with that if you're interested. You can see triplet oxygen is just simply more stable, has a lower energy than that of singlet oxygen. Now, the issue here, though, is singlet is the default setting for oxygen. So you need to make sure that you set oxygen to be a ground state triplet, or that it has 2 unpaired electrons. So when you're going through your setup menu, in fact, let me show you in WebMO. So if we go to the job manager, let's actually build O2 so we can get a sense of what that looks like. So it's just taking a second or two to load. We just want to be able to show and get the correct data for O2. So we go to our periodic table. Let's actually just create an atom. Oh, clicking on the periodic table. So go to O, click drag again for the double bond, forward arrow. Remember, we're going to be using Gaussian as our engine for our calculations. There's not a whole lot special about which engine you choose. It's just you want to choose one that's going to be consistent throughout the experiment for all the general calculations we want to do. The thing that's really important is that all of our engines that do a calculation, say at whatever method, should provide the exact same results. So like the engine we're using shouldn't give us different results. It may just give us the access to a consistent set of basis sets and theories and calculation types that we need to be able to run for our molecule. So we're going to be doing optimizations and vibrational frequencies because we need our thermodynamic data to get H's and G's, the enthalpies and the Gibbs energy of these molecules. And so here's where we choose the multiplicity. So here's where we need to choose a triplet for O2. But then for all the other molecules here, we'd want to choose singlets. And if we ever need to do a calculation on a charged molecule, which we don't through this activity thus far, we would put that charge in right here. So in case you're wondering, where do we put charge in? The answer would be in the calculation setup menu. And then we would run our calculation on triplet O2. And so here we're reporting the delta E. So this would be taking the electronic energies, tabulating those for all the molecules, taking the delta H's and the delta G's. So do each of your calculations on each isolated molecule. So build each molecule separately, run a calculation separately, report the, so it says to evaluate the delta EH. So we're extracting electronic energy, enthalpy 298K, and the Gibbs energy 298K. This is a dipole moment too. I don't think we ever do much with a dipole moment here, but these are kind of some of the values that I think are important to grab from a calculation almost anytime you run it, and throwing those into an Excel spreadsheet would just be a good idea. And so what you're probably going to find is that these methods don't work so well. It's almost intentional. I kind of wanted to choose reactions that are somewhat tricky to model. So what's really hard here, and maybe seems not entirely obvious, is that the bonding environments are really different in our reactants and products. So if we want to get good agreement in from our computational results to the literature results, and let me mention one other thing here with the literature results. Usually you got to get your entropy data for these molecules out of like a Gen Chem textbook. So if you have a Gen Chem textbook handy, look up your entropy data that you need to know to determine literature, delta G's, and if you can't find that data, just simply cross it out or just say couldn't find. It's a little bit hard to find. You may have to go to like the CRC. You can get to it through our library link. Maybe we can talk about that later if we need to. That might be another place to find some of the entropy data, but it's always been somewhat tricky to find the entropy data without having to search under every rock in the world. But the next part looks at two different reactions here. So let's say we have formaldehyde plus propane goes to acetaldehyde plus ethane, and then the next reaction looks at acetaldehyde, adding another methyl group. So what this is kind of comparing here is, does a methyl group more stabilize an alkyl chain or an aldehyde group? And if the methyl group didn't stabilize the aldehyde group better or worse than itself, then this delta H would just be equal to 0. So you can get a sense here in reaction 1 of whether the methyl group better stabilizes a formaldehyde group or itself or neither by seeing if this reaction has a negative, close to 0, or slightly positive delta H. So you can get a sense of which side of the reaction is favored, where the methyl group is favoring its stabilization. And you can do it again. You could take the acetaldehyde plus another methyl group. And so if we were really looking at the previous set of calculations that we tried that maybe didn't work out so well as a means of comparing how stable acetaldehyde is compared to formaldehyde, or how much stability a methyl group really adds to an aldehyde group, the previous experiment wasn't even going to really address that question. This set of reactions here can actually address that question perhaps a little bit more directly. And it also is going to keep the bond types the same. One of the things about reactions 1 and 2 here is they are what we call isodesmic reactions, meaning their bond types are identical on both sides. Both sides of the reaction have identical numbers of CH bonds, CO double bonds, CC single bonds. So if you notice, the bonding type is much more similar in reaction 1, reactants and products, and likewise for reaction 2. So I think you're going to find that reactions 1 through, actually, I guess it says 1 through 3, but reactions 1 through 2 are going to be modeled probably much more accurately here. So do the same thing where you build each molecule separately. You've already done formaldehyde and acetaldehyde. You don't need to do those again. So we really only need to do propane and ethane. And then determine our delta H, E, and G for those reactions. One thing I do want to mention that sometimes confuses students in this experiment, like when you do a calculation on O2, like O2 gas, in terms of its literature value for its delta H, like the enthalpy of formation of O2 is defined to be 0. But when you do your computational calculation, you'll find that the computed enthalpy of O2 is far from 0. It's actually very negative. The issue here is that the referencing of each of our calculated enthalpies is a different, it's on a different scale than your tabulated enthalpies of formation. But as long as you take into account stoichiometry correctly, take the correct calculation of products minus reactants, then you should get an accurate result, assuming that your computed enthalpies are actually accurate. Now, the issue here is that the computational methods report the total or like the absolute enthalpy of the molecules and do not reference them. The computational methods don't reference the enthalpies relative to the elements in their standard state set to zero, like tables of thermodynamic values tend to do. So note that we have a different standard scale, if you will, but that the tabulation of delta H's of reaction should be, those don't depend on what scale we're using, as long as our products and reactants are of the same scale or done with the same method. So hopefully this isn't too confusing. It just means that you can take computed thermodynamic data referenced to the elements in their standard state set equal to zero, use those to calculate a delta H of reaction, and compare those against computational results, which are in a different standard scale, but then still take the products minus reactants and get delta H's that should compare. As long as the results are accurate, they should compare well. So look at the new reactions. How do they do? How does the methyl group actually stabilize the carbonyl group? What about the second methyl group? And then in the case of acetone versus propanol, you can actually do a direct comparison since they're isomeric. Whenever we're comparing isomers, we can more easily just calculate the energy of one of the molecules, build the other molecule, calculate its energy, evaluate which one's lower energy and hence more stable. So we can look and compare the aldehyde and ketone here and see which one of the same formula is more stable. Okay. I actually think day 2 is pretty, that you should be able to finish day 2 pretty quickly. So if you want to jump ahead, you can into day 3. If you want to wait for day 3 to do activity 3, you can do that as well. I'll introduce this experiment or this activity in a separate video. All right, thanks for the attention.